Find the effective length factor K for column BE. In this problem, a three-story structure experiences a compression load of 180 kips in member BE. The lengths of all columns and girders are provided, as well as the exact I-beam type for 6 of those steel members. The effective length factor, as part of a structural frame, is determined by knowing the end condition coefficients of that member, which for this problem refers to joints B and E. The end condition coefficients equal the sum of the rotational stiffness values in the columns divided by the sum of the rotational stiffness values in the girders. Since it's safe to assume the moduli of elasticity is constant, then these terms cancel out and we're left with the area moment of inertia, I, and the length of the member, L. In the event member BE is inelastic, then the end condition coefficient at a joint equals tau times the elastic end condition coefficient for that joint. We'll begin by evaluating lambda c, the slenderness parameter, which equals KL over R times pi times root Fy over E. Since we're interested in member BE, we'll add subscripts BE to the equation. From the problem statement, we know the yield stress in the steel equals 36 KSI, which is the same as 36,000 pounds per square inch. And it's generally assumed the modulus of elasticity for steel equals 2.9 times 10 to the 7th pounds per square inch. We can determine the length, L, by looking back at the structure, locating column BE, and noting its length is 12 feet or 144 inches. For a W10 by 33 steel member, the radius of gyration about the strong axis equals 4.184 inches. The last unknown variable is the effective length factor, K, which is the variable we're solving for. So we'll compute lambda c as 0.3860 times the effective length factor in column BE. Since this doesn't answer our question regarding which equation to use, we'll assume lambda c is greater than 1.50 and compute the end condition coefficients using the top equation. Then, using those values, we'll compute the effective length factor, K, for member BE, and then check our assumption that lambda c is greater than 1.50. The end condition coefficient for joint B is computed by plugging in the appropriate lengths and plugging in the area moment of inertia values about the stronger axis. The end condition coefficient at joint B equals 1.52. Joint E is computed in a similar manner. After plugging in the lengths and area moments of inertia, the end condition coefficient at joint E equals 1.35. Keep in mind, these two end condition coefficients refer to an elastic condition in the I-beam. Therefore, we can determine the effective length factor if lambda c is greater than 1.5 by marking out GB and GE on the effective length alignment chart, and the assumed effective length factor equals 1.43. Now we can check our assumption regarding lambda c, which equals 0.3860 times 1.43, or 0.552, which is less than 1.5. Therefore, we know the end condition coefficients we calculated must be multiplied by tau, so we can find the inelastic end condition coefficients. From before, we know GB and GE for the elastic case, and tau represents the stiffness reduction factor, which can be determined using the stiffness reduction alignment chart, where the elastic and condition coefficients are plotted out as before, and tau BE equals 0.83. Plugging in 0.83 for tau, the inelastic and condition coefficients for joints B and E equal 1.26 and 1.12, respectively. Now we can return to the effective length alignment chart, plug in the two inelastic and condition coefficients, and the effective length factor for member BE equals 1.37. When reviewing the possible solutions, the answer is B.